In this video, we're going to look at another application of work integrals. According to Newton's law of gravitation, two bodies with masses m1 and m2 attract each other with a force of F is equal to gm1 m2 divided by r squared, where r is the distance between the centers of the two bodies, g is the gravitational constant of the universe. Part A of the question asks us to use Newton's law of gravitation to find the work required to launch a 500 kilogram satellite vertically to an orbit 2,000 kilometers high. That means we're launching this satellite from the surface of the Earth at ground level up to a height of 2,000 kilometers. Mass of Earth is 5.98 times 10 to the 24 kilograms. Radius of Earth is 6.37 times 10 to the 6 meters. And the gravitational constant of the universe is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. These are constants that we need to use in our calculations. Part B of the question asks us to find the work done in raising the orbit of this 500 kilogram satellite from 2,000 kilometers to 3,000 kilometers. That means the satellite is at a 2,000 kilometer orbit around the Earth, and we would like to find the work done against gravity to raise the orbit of this satellite from 2,000 kilometers to 3,000 kilometers. And we're going to apply a work integral to solve for that. So what we're going to do is let's simplify Newton's formula. Newton's formula is F is equal to G m1 m2 divided by r squared. We will simplify this to F is equal to K m2 divided by r plus y squared. It is still the same formula. We just group some constants together. For example, k is equal to gm1. So g is the gravitational constant of the universe, and m1 is the mass of Earth. That's not going to change, so we just grouped it together, call it k. And r is the radius of Earth. Y is the distance of the satellite from the surface of the Earth. So now it's a bit easier. When y equals 0, we're at ground level. And m2 is the mass of the satellite. All right. So let's look at part A. Find the work done in launching this 500 kilogram satellite to an orbit 2,000 kilometers high. The force of gravity, the force between two objects, according to Newton's law, is km2 divided by r plus y squared. This is the force of attraction between a satellite and Earth. dW is equal to km2 divided by r plus y squared, force times distance, times dy. dy is the distance. So work is equal to integral from y equals 0 to y equals 2,000 kilometers. dw, this is equal to, we have to change the units to meters, so y equals 0 meters, and 2 million meters with 6 zeros. And the mass of the satellite is 500 kilograms. This is 500. So we get 500k divided by r, radius of Earth, plus y, distance from the surface of the Earth, all squared, dy. We're going to apply U substitution to solve this. Let u be equal to r plus y. Differentiate both sides with respect to y. Derivative of capital R is just 0 because it's a constant. Plus, and derivative of y is just dy. So du is equal to, let me just write that as du equals dy. It's neater this way, and let's label this as U substitution. All right, so what we get is work is equal to 500k is a constant, passes right through the integral. So we get 500k. And integral of 1 over r plus y squared with respect to y, applying U substitution, is going to be minus 1 over r plus y. And the limits of integration are 0 to 2 million meters. Now we're going to apply fundamental theorem of calculus, and we will get minus 500k times 1 over r plus 2 million meters minus 1 over r plus 0 meters. All right, so now let's substitute. R is equal to 6.37, the radius of Earth, times 10 to the 6 meters, and the constant k, which is gm1, the gravitational constant times the mass of the Earth. So this is going to be 6.67 times 10 to the minus 11. That's capital G, and the mass of the Earth is 5.98 times 10 to the 24. If we put this into a calculator, we're going to get K is equal to 39.89 times 10 to the 13. So let's substitute K and capital R, make our computations easier. So we get minus 500 times 39.89 times 10 to the 13 times 1 over capital R, radius of Earth, that's 6.37 times 10 to the 6 plus 2 times 10 to the 6, which is the orbit of the orbit of the satellite, 2,000 kilometers, which is 2 million meters, 2 times 10 to the 6 meters, minus 1 over 6.37 times 10 to the 6 meters. All right, if we work this out, we're going to get work is equal to negative 19945 times 10 to the 13. And if we decimalize all of this, we're going to get 0.12360119 minus 60157. And if we put this in the calculator, we'll get 7,757,9,100,123. So we have essentially almost 7.6 billion joules of work is required. That's a lot of work that's required. 7.6 billion joules of work is required to lift this satellite from ground level to a height of 2,000 kilometers above the Earth. Now, part B of the question asks a different question. Find the work done in lifting this 500 kilogram satellite from an orbit of 2,000 kilometers to 3,000 kilometers. So we want to increase its orbit. Its orbit initially is at 2,000 kilometers, and we would like to find the work done against gravity to change the orbit, to lift the orbit to 3,000 kilometers. So we start with the force formula, Newton's formula, F is equal to K m2 divided by r plus y squared, where m2 is the mass of the satellite, is 500 kilograms, and K, of course, is equal to G times m1, the gravitational constant of the universe, times the mass of the Earth. So the work is going to be the integral from 2 million meters, 2,000 kilometers, which is 2 million meters, to 3 million meters. And the force function is 500K divided by r plus y, all squared dy. We apply U substitution as like before, U sub. Let U be equal to r plus y. Differentiate both sides with respect to y. We get du is equal to dy. All right, so the work is going to be, work will be equal to minus 500K divided by r plus y, applying U substitution, and evaluated from 2 million meters, which is 2,000 kilometers, to 3,000 kilometers, which is 3 million meters. And K is equal to GM1, which is 39.89 times 10 to the 13. And R is the radius of Earth, which is 6.37 times 10 to the 6 meters. We're going to substitute these in and solve for the work. So work is equal to minus 500K divided by R plus Y. Work is equal to minus 500 times K. Well, the value of K is 39.89 times 10 to the 13. And times 1 over R plus Y. So that's going to be 6.37 times 10 to the 6. This is radius of Earth. Plus 3 times 10 to the 6 meters. That's 3,000 kilometers. Minus 1 over 6.37 times 10 to the 6 plus 2 times 10 to the 6. This is a plus. Close off the bracket here. So the work done, if we decimalize all of these, is going to be 2,393,400,000 joules, if we were to put this into a calculator. Let's just double check everything we've got there. Yes, that works. So that's approximately 2.4 billion joules. Billion joules means 9 zeros. 2.4 billion joules of work is needed to raise the orbit of this 500 kilogram satellite from an orbit of 2,000 kilometers above the Earth to 3,000 kilometers above the Earth. And this work was done against gravity, of course. All right, thanks.